Welcome to today's cosmic journey, where we dive deep into some of the most baffling astronomical discoveries of our time. Recently, the James Webb Space Telescope, JWST, has turned our understanding of the cosmos on its head with a groundbreaking observation: a galaxy resembling our own Milky Way, in a state that challenges our current notions of the universe's age. Buckle up as we explore this enigmatic find and its implications. Is the universe actually 7 billion years old instead of the previously believed 13.8 billion? This dramatic reevaluation stems partly from the discovery of a galaxy strikingly similar to the Milky Way, which, according to existing theories, shouldn't even exist. The James Webb Space Telescope has revealed numerous advanced galaxies in the early universe, shortly after the Big Bang. These findings strongly suggest that our previous theories might need substantial revision. Does this new estimation of the universe's age provide the definitive answers we seek, or does it introduce even more unsolvable questions? The James Webb Space Telescope has cataloged over 1,000 galaxies that resemble our Milky Way in their early stages, observed from a few 100 million to 1 billion years post-Big Bang. This discovery challenges the long-standing belief that disk-shaped galaxies were a rarity or even impossible during that epoch. Disk shapes, believed to result from frequent galactic collisions, seem improbable at a time when the universe and its galaxies were just beginning to form. This poses a significant contradiction. How could there have been numerous collisions when the universe was still in its nascent stages? The enigma deepens, suggesting that the universe might be far more complex than we ever imagined. The galaxies uncovered by the James Webb Space Telescope defy expectations. They are too mature and intricately organized for their cosmic age. If we apply traditional models of galaxy development to these findings, it would imply that these galaxies formed before the Big Bang, over 13.8 billion years ago. Remarkably, researchers discovered 3,156 galaxies in what initially appeared to be just a collection of irregular star clusters from the universe's infancy. From this group, 1,672 have been classified as disk galaxies, based on the exceptional spectrometer analyses provided by the Webb telescope. This indicates that such structured galaxies were not rare anomalies, but were instead relatively common when the universe was merely a few 100 million years old. These groundbreaking discoveries necessitate a complete reassessment of how galaxies form and evolve. Previously, it was assumed that large and highly structured galaxies could only originate from the collisions of smaller dwarf galaxies. However, these findings challenge that notion, suggesting a much more complex narrative of cosmic evolution. The latest research, published in the Astrophysical Journal, underscores the need to rethink our understanding of the universe's early days. These revelations emphasize the significance and scientific potential of the new telescope, compelling us to urgently revise our long-standing theories. The fresh insights into galactic evolution and the unexpected prevalence and organization of disk galaxies in the early universe challenge our core assumptions about the Big Bang and other foundational concepts in astrophysics. A key highlight in this research is the discovery of the galaxy Sears 2112, named after the Cosmic Evolution Early Release Science Survey. This galaxy, observed as it existed just 1.5 billion years after the Big Bang, bears striking resemblance to our own Milky Way, a galaxy that took billions of years to develop its distinctive spiral arms. The existence of such a mature galaxy at this early stage defies previous theories, which suggested that disk galaxies like the Milky Way emerged much later in cosmic history. Sears 2112 not only challenges these traditional views, but also prompts us to reconsider how galactic structures might have evolved more rapidly and earlier than we previously believed. One of the most puzzling aspects of Sears 2112 is its well-preserved, orderly disk structure at such an early point in the cosmos. This is contrary to expectations that young galaxies at this time would be irregular and tumultuous. The discovery of Sears 2112 raises profound questions. How did this galaxy acquire its shape, and what unknown conditions in the early universe allowed for such an advanced development? If we apply our old models of galaxy evolution to Sears 2112, we're left with a paradox. This galaxy appears to have formed at a time when, according to previous scientific understanding, the universe itself shouldn't have existed. These groundbreaking discoveries have prompted some scientists to reassess the age of our universe, leading to some truly astonishing results. They raise a provocative question: is the Big Bang Theory fact, or could it be fiction? Surprisingly, there has been as much evidence challenging the Big Bang as supporting it. However, the longevity and acceptance of certain theories often cast them as near absolute truths, causing some scientists to overlook alternative explanations for cosmic phenomena that are equally plausible. Despite growing discrepancies and gaps within established models, researchers had long clung to ideas ratified since the 1920s. According to the Big Bang Theory, the universe began about 13.8 billion years ago as an immensely hot and dense soup of protons, electrons, and other elementary particles. For the first 380,000 years, the universe remained too hot for atoms to form, existing primarily as a sea of ionized plasma. As it expanded, the universe cooled, reaching a point where atoms could finally begin to form. This steadfast adherence to traditional theories is now being challenged by new findings, suggesting that our understanding of the universe's early days might need a radical overhaul. How did these early galaxies form so quickly and maintain such complex structures? These questions hint at the possibility of undiscovered processes at play in the early universe, urging us to rethink everything we thought we knew about cosmic history. About 2,630 years after the Big Bang, protons and electrons combined for the first time to form neutral hydrogen atoms during what is known as the recombination event. The cosmic microwave background, which serves today as a cosmic map, originated in this period. It has been instrumental in helping us piece together the universe's early history. In the 100 million years following recombination, the universe entered the Dark Ages, a period devoid of stars and galaxies, cloaked in darkness and composed primarily of neutral hydrogen and helium. Yet, it was during this seemingly inert phase that the seeds of the universe's future were sown. Density fluctuations within the universe gradually led to the formation of massive gas clouds, which grew denser under their own gravity. These early ripples in density can still be observed today as tiny variations in the temperature of the microwave radiation permeating the universe. These subtle clues have allowed us to deduce the large-scale structures of the cosmos. Around 100 million years post-Big Bang, the first stars, known as population 3 stars, began to ignite. These stars were colossal, with masses ranging from tens to thousands of times that of our Sun, and they burned with an intense brightness. Their brief lifespans ended in spectacular supernova explosions, scattering new elements across the cosmos, paving the way for the rich, complex universe we observe today. These supernova explosions dispersed heavy elements and gases throughout the universe, providing the building blocks for new stars and galaxies. The first galaxies likely formed from the contraction and merging of smaller gas clouds and protogalactic clumps. These early galaxies were probably chaotic and small compared to today's massive, well-organized structures. Over time, continuous star formation and galactic mergers led to the development of larger and more structured galaxies. Thanks to the James Webb Space Telescope, JWST, we can now observe galaxies that existed just 250 million years after the Big Bang. Remarkably, these galaxies are so developed and structured that they appear as if they have undergone billions of years of evolution. This discovery opens up three intriguing possibilities. Either the Big Bang never happened and the universe is eternal. The Big Bang occurred much earlier than previously thought, making the universe significantly older, or stars and galaxies evolved at an accelerated pace. Gupta, a scientist at the University of Ottawa in Canada, has proposed that the universe is 26.7 billion years old. Did you think it would be so straightforward to determine a new age for the universe? Gupta's research is challenging our understanding of cosmic history, suggesting that our universe may be far older and more complex than we ever imagined. Alternative models of cosmic expansion, dark matter, and dark energy have long been topics of debate. None of these elements, uniform expansion, dark matter, or dark energy, have been definitively proven, raising questions about their actual existence. The groundbreaking images and discoveries from the James Webb Space Telescope have emboldened Gupta in his unconventional ideas. Gupta was among the first scientists to boldly reassess the age of the universe. Gupta's new approach contrasts sharply with traditional methods that rely on cosmic background radiation and the Hubble constant. The Hubble constant measures the universe's rate of expansion and has been pivotal in previous age calculations. However, different measurement techniques have yielded varying values for the Hubble constant, leading to the so-called Hubble tension. This tension suggests that the universe's expansion rate is not uniform, conflicting with the Big Bang theory's notion of space consistently drifting apart. To address this discrepancy, Gupta has developed a novel approach. He challenges the old models and proposes a new perspective that may redefine our understanding of the cosmos. His research aims to resolve the inconsistencies and offer a more accurate estimation of the universe's age, potentially revolutionizing the field of cosmology. Gupta has developed a model introducing alternative cosmological parameters and redefining the effects of dark energy and dark matter. According to his new parameters, the universe might be expanding much more slowly or in a non-linear fashion. A slower expansion model implies an older universe to account for the observed degree of expansion. An irregular expansion might suggest unknown structures and forces or even multiple starting points for the universe. A central element of Gupta's theory is the modification of the general theory of relativity. He hypothesizes that the physical behavior of dark energy has changed over time, potentially explaining the variations in expansion rates. This implies that dark energy is more dynamic and mutable than previously believed. In his initial recalculations, Gupta estimated the age of the universe to be 26.7 billion years. He also presented an alternative calculation suggesting the universe could be as old as 42 billion years. Additionally, Gupta revisited Fritz Zwicky's 1920s theory of tired light, which posits that light loses energy over vast distances, a concept that had fallen out of favor but might offer further insights into the true age and nature of the universe. Gupta's innovative approach challenges traditional cosmology and opens up new possibilities for understanding the cosmos. His work encourages us to rethink long-held assumptions and consider that the universe might be far older and more complex than we ever imagined. Gupta's theory, which has received little scientific attention until now, posits that the wavelength of light changes as it travels through the cosmos. If true, this would likely mean that all our previous calculations regarding the age of the universe and the distances within it are incorrect. A universe nearly twice as old as previously thought would easily explain the existence of galaxies like Sears 2112 and other highly evolved galaxies seen in Webb's images. Gupta's model could also clarify why some observations of distant galaxies and quasars are challenging to reconcile with the current cosmological model. However, the scientific community has been slow to accept Gupta's recalculations. Most conservative branches of astrophysics still adhere to the Big Bang theory, which places the universe's age at 13.8 billion years, and they prefer explanations suggesting that stars and galaxies formed much faster and differently. In an unprecedented observation, the JWST has identified what appears to be a distant galaxy that mirrors the Milky Way in structure and composition. This discovery is pivotal as it seems to suggest that this galaxy, and possibly others, are much older than the universe as we currently understand it, dating back as much as 26.7 billion years. Let's unpack how astronomers came across this phenomenal find and what tools were instrumental in this revelation. The existence of such a mature galaxy within the observable universe poses a significant puzzle. How can any celestial body be older than the universe itself? This segment delves into the implications of this finding on the Big Bang theory and the universally accepted age of the universe, which is currently estimated at about 13.8 billion years. We'll explore the theoretical adjustments that might be necessary if this observation holds up to further scrutiny. How did the James Webb Space Telescope manage to identify such a distant object? This part of our discussion focuses on the cutting-edge technology and instruments aboard the JWST that allow astronomers to peer back almost to the origins of the universe. From infrared capabilities to advanced spectroscopy, learn how this telescope is reshaping our understanding of deep space. What makes this galaxy a doppelganger of the Milky Way? Here, we compare the structural and chemical characteristics of the two galaxies. By understanding the similarities, researchers hope to glean insights into our galaxy's formation and evolution, and by extension, the evolution of galaxies in general. What next? This closing segment outlines upcoming missions and research projects inspired by this discovery. With the astronomy community buzzing, future telescopes and missions are already being planned to further investigate these early galaxies. The potential to fundamentally alter our cosmic perspective is immense, as new tools and technologies are poised to come online. How have scientists estimated the age of the universe thus far? This segment delves into the historical methodologies used, from studying the oldest known stars to measuring the expansion rate of the universe, known as the Hubble constant. Each method provides a piece of the cosmic puzzle, contributing to our current understanding that the universe is approximately 13.8 billion years old. We'll examine how these traditional methods might be reconciled or challenged by new data. In the quest to understand the universe, dark matter and dark energy remain elusive yet dominant forces. This part of our discussion explores how these components, which make up about 95% of the total mass energy content of the universe, influence cosmic structures and expansion. Could they play a role in the existence of an anomalously old galaxy? We'll look at current theories and recent findings in cosmology. With new findings come new theories. This segment introduces some alternative cosmological models that have been proposed in light of recent discoveries. From multiverse theories to modified laws of gravity, we explore how these ideas attempt to explain phenomena that don't quite fit into the standard cosmological model. How exactly do astronomers date galaxies billions of light-years away? This segment breaks down the tools and techniques used, from redshift measurements to spectral analysis. Understanding these tools will clarify how scientists are able to estimate the age of distant galaxies and potentially revise those estimates in the face of new evidence. This discovery could reshape the field of cosmology. Here we discuss the broader implications for astrophysics if the age of the universe needs to be reconsidered. From textbook revisions to new research directions, the impact spans educational, theoretical, and observational aspects of astrophysics. What has been the reaction in the scientific community and among the general public to this groundbreaking discovery? This segment covers the debates, discussions, and excitement this revelation has sparked. We also touch on how such news is communicated and perceived outside the scientific circles. We owe these discoveries to not just brilliant minds, but also groundbreaking technology. This segment focuses on the technological advancements that have led to these kinds of discoveries. From the development of space-based telescopes like the Hubble and the JWST to advancements in computational models used in simulations and data analysis. Every major scientific discovery has philosophical implications. This segment reflects on how findings like these influence our understanding of time, existence, and our place in the cosmos. How do such discoveries impact philosophical inquiries about the universe and everything within it? As these new cosmic discoveries unfold, educational and outreach efforts must also evolve. This segment discusses how new astronomical discoveries are integrated into educational curriculums and public outreach programs, aiming to ignite curiosity and understanding of the universe among students and the general public. Astronomical discoveries are often the result of extensive international collaboration. This segment highlights how scientists and institutions from around the world work together to share data, resources, and expertise. The discovery of the Milky Way Doppelgänger, for example, involved contributions from various space agencies and research teams across the globe, showcasing the power of global cooperation in advancing our understanding of the universe. Despite advanced technology, observational astronomy still faces numerous challenges. This segment delves into the difficulties astronomers encounter, such as dealing with cosmic dust that obscures observations, the need for precise instrumentation calibration, and the limitations of current technology. Understanding these challenges helps appreciate the monumental efforts behind each discovery. Every new discovery in astronomy sparks the age-old question, are we alone in the universe? Welcome to Blasovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blasovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe. Live Q&A sessions with experts. Your membership will grant you the chance to participate in live Q&A sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos, and join us in unraveling the secrets of the universe. Become a Blasovia Science TV member today, and together, we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comments.